Let's come to the influence of the pore fluid pressure. In most rocks we find space between individual crystals, and these spaces are typically filled with hydrous fluids. This particularly applies to rocks in the deeper part of the brittle crust, and fluids have very different physical properties compared to the solids in which these small spaces are contained. The most important difference is that the thermal expansion of hydrous fluids is much higher than the expansion of minerals. This means when the rock heats up or more fluid is created, the fluid pressure increases more strongly than the pressure of the solids in which these fluid cavities exist. A further point is that the fluids themselves do not have any shear resistance, but since they are a part of the rock, they will reduce the overall shear strength. Because even if the rock contains hard minerals like quartz and feldspar or garnet, the proportion of the fluid will reduce the shear strength because there is a part of the rock that is mechanically very weak. The point is that when fluid pressures increase more strongly than the pressure in the solids, the fluids will impose an outward acting stress. These are little cavities with fluids that try to expand more than the space volume increases in which they are contained, and that would impose an outward acting stress. So imagine small droplets of fluid in a rock that are pushing outwards against the stress that acts on the rock. That is the reason why, in order to obtain mechanically effective stresses, we need to subtract the pore fluid pressure from all other stresses, such as sigma 1, sigma 2 and sigma 3. Mechanically effective stresses are symbolized by sigmas with a little star. For instance, sigma 1 star would indicate that the fluid pressure already has been subtracted from that stress. We will see that this has profound consequences for joint, vein and dike formation. Let's assume a stress condition as we see it here, indicated by this orange Mohr circle. We have a certain sigma 1, somewhat smaller sigma 3, but we can see that the stress conditions are by no means critical. This rock would be perfectly stable because it is far away from any of our failure envelopes. Even if we would plot our envelope of sliding friction into this diagram at a slope angle of 40 degrees, this Mohr circle would be far away from that, and therefore this is a stable stress condition. However, if we now produce more fluid or we heat up the rock, then the fluid pressure in this rock will increase, and we will have to subtract the magnitude of the pore fluid pressure from both sigma 1 and sigma 3. That would mean that with increasing pore fluid pressure, our Mohr circle effectively would move to the left-hand side. And eventually, if the pore fluid pressure becomes large enough, we would intersect the tensile failure envelope. Again, this does not mean that this rock would come from the depth to the surface, but because the fluid pressure counteracts the absolute stresses, the rock would behave as if it was at the surface or close to the surface. And under such effective stress conditions, that means a sigma 3 star and a sigma 1 star, these conditions are suitable for tensile failure. And what would happen is a tensile fracture would form. the fluid would be extracted into that fracture and a vein can form. In particular, a vein can form because on that fracture a tensile stress acts. That makes it suitable for dilation. So let's have a look again. We have stress conditions. Fluid pressure builds up by fluid generation or by heating up the fluid, and this moves our effective stress conditions towards tensile failure. Here we come back to this diagram that we have seen before, and you remember we were discussing whether actually it is justified to draw these inward pointing the sigma 3 vectors, because that would imply that we actually have compressive stresses, and that was contradicting our requirement that sigma 3 has to become negative in order to cause tensile fractures. We now see here that these outward pointing stress vectors might relate to the effective stresses that act, because we see here the total stresses remain compressive. We are deep in the crust. We have only all-side compressive stresses simply because of the kilometers of rock that overlie this place. But the fluid pressure counteracts these stresses and allows us to have effectively tensile stresses, and these tensile stresses allow to fracture the rocks. In this context, another point is very important. Let's consider a situation where we have no tectonic stresses at all. We have a totally stable crust that passively undergoes heating, and this would mean that under hydrostatic stress conditions, where sigma 1, 2 and 3 are the same, we normally would never be able to achieve any kind of deformation. But if fluids are present and the fluid pressure increases sufficiently, and we do that stepwise with release of fluids due to metamorphic reactions, for instance, where hydrous minerals are replaced by non-hydrous minerals, that might increase the fluid pressure in addition to increasing temperature. The fluid pressure could increase to such an extent that tensile fractures and veins may form under perfectly hydrostatic stress conditions. That is a very important mechanism to form hydrothermal vein networks in absence of geologically relevant tectonics or any mountain building processes. It can happen simply by fluid generation under thermal heat input. Let's assume another situation. Again, we have a perfectly stable stress situation, but now our differential stress is a little bit larger because sigma 1 is substantially higher than sigma 3. Again, under dry conditions, no deformation can take place, but we see here with increasing fluid pressure, again, we will intersect with a failure criterion. In this case, this is the transitional tensile failure envelope, the parabolic failure envelope, and that intersection will produce conjugated fractures. As we have seen before, these fractures are exposed to a tensile normal stress, and that means they do not only shear laterally, they also open up. And this opening of these joints allows dilation, and it allows the fluid to escape and to precipitate hydrothermal veins. This is now a different kind of vein. These are conjugated fractures. They have a lateral shearing component because you see here at the intersection point we can look horizontally to the shear stress axis, and we will find here a positive and a negative value. That means two conjugated shear fractures form with opposite senses of shear. Obviously, we try the same exercise with larger differential stresses, again starting with stable stress conditions that are not likely to produce any kind of fracturing under dry conditions, but with the generation of fluids and increasing fluid pressure, our effective Mohr circle will move to the left and will eventually intersect with the failure criterion, but now this is the Coulomb failure envelope. And what we can see here is shear stresses are acting. They are opposite in shear sense for the two conjugated sets, but the normal stress that is acting on these fractures is compressive. And that means we cannot dilate these fractures in order to form veins. That is an important difference at large differential stresses. Our Mohr circle will not fit into the narrow space of the parabolic failure envelope, or will not be small enough to reach the tensile failure envelope. And that would mean Coulomb fractures will form. Perhaps fluid can escape along these fractures, but we cannot dilate the fractures to form visible and meaningful hydrothermal veins. This is an important information for everybody working in hydrothermal systems, in hydrothermal ore deposits. One should be aware that these veins cannot form under the peak of tectonic deformation, when differential stresses are very high, when, for instance, faults are forming or folds are forming. Vein formation is only possible under relatively small differential stresses that allow intersection of either the parabolic or the tensile failure envelope. Only under these conditions, hydrothermal veins are actually able to dilate and form meaningful structures. What happens after fracturing and fluid escape? Obviously, once you extract the fluids that were responsible to create the vein itself, the fluid pressure will drop. And once the fluid pressure drops to lower levels and perhaps to zero, the effective Mohr circle moves back to the right to the dry conditions, and no more fracturing is possible. What needs to happen is that the pore fluid pressure rebuilds, perhaps by the release of new fluids, perhaps by increasing temperature. And this process can alternate repeatedly until the fluid system or the generation of fluids comes to an end. The resulting structure might be veins that follow a crack-seal process. These could be multiple episodes of fractures. Whenever sufficient fluid pressure is regenerated, the existing vein might fracture, and a new bit of the vein, a new zone in the vein might be generated, and new material precipitates, and that again will seal the fracture, make it impassable for fluids, and we need to refracture it after sufficient pore fluid pressure has been generated in the host rock. Let's summarize what we have learned about the influence of pore fluid pressure. Here on this stress strain diagram, we can see that high pore fluid pressures are weakening the rock, because high pore fluid pressure will counteract the compressive stresses, and that might cause the rock to fail at fairly low differential stresses, after which veins can form. When we decrease the fluid pressure here, for instance, to 150 megapascals, the rock will become harder to break. And we see with further decrease in fluid pressure, here this experiment has shown that the highest differential stresses are required for dry rocks, for rocks with zero pore fluid pressure. All these experiments are run under otherwise identical conditions and in the low temperatures, but the principle is clear. High pore fluid pressures weaken the rock. So what we learn from increasing pore fluid pressure, it may decrease the shear strength and may cause hydraulic fractures in conditions that under dry conditions are totally uncritical. We see that depending on the magnitude of the differential stress that is present, all failure types are possible. Small differential stresses would lead to tensile failure or transitional tensile failure. At higher differential stresses, Coulomb failure would be possible when the pore fluid pressure increases. Even under hydrostatic stress conditions, failure is possible if the pore fluid pressure reaches critically high levels. And this may simply be driven by fluid generation or heat influx, or typically a combination of both. The vein formation, however, is only possible if we can dilate the fracture that forms, and that requires either tensile or transitional tensile failure. Hydraulic Coulomb fractures might release fluid stress because there might be a pathway for fluids to escape along the fractures, but a dilation of Coulomb faults is not possible because on Coulomb faults, after their formation, there is still a compressive normal stress acting that prevents this dilation. When we examine hydrothermal veins, it is advisable that the first feature that you should examine is the growth direction of quartz fibers or any other fibers that form, but typically we see these features in quartz veins. Very often quartz fibers are growing from the boundaries of the fracture inwards, or perhaps also in the opposite direction, from inwards outwards, but in the direction in which this fracture opens. And if we are looking at mode 1, tensile failure, the fibers of quartz would grow perpendicular to the fracture surfaces. If you observe fibers growing in that direction, you have good evidence that this is a mode 1 fracture, and that this fracture must have formed either under hydrostatic conditions or under small differential stresses, because the tensile failure envelope was intersected. So the opening direction in this case would have been as indicated by this arrow. If you observe obliquely growing fibers, quartz fibers in such a vein, you have good evidence that we have a component of tensile opening and a component of lateral shearing, and that would indicate transitional tensile failure. The presence of a vein tells you that there is a tensile component, and the obliqueness of fibers would indicate that there is a lateral shearing taking place, and that gives you evidence that during the formation of this vein, the parabolic failure envelope was intersected and transitional tensile failure took place. Would it be possible that Coulomb failure is responsible for the formation of this vein? No, certainly not, because the dilation requires a tensile and therefore a negative normal stress acting on that, and if the Coulomb failure envelope would have been intersected, this normal stress would have been compressive and positive, and on the right hand side of the origin of the Mohr stress diagram. This is all that I have to tell you for now about the Mohr stress diagram. If you like that lecture series, you might consider to like or to comment or to subscribe. Comments are always welcome because it helps me to improve perhaps the next edition of this lecture series. For now, thank you very much. Until we meet again.